talk. Now I invite. So a lot of thanks to you, Professor Casillo, for a wonderful talk. Now I invite Dr. D. Datto to chair the talk of Professor S. Kaur. That is our next talk. Professor D. Datto. He was here. আপনি ইন্ট্রোডিউস করুন।
Hello, good morning to everybody. That I think that I hope I am audible, right?
Yes, yes.
Okay.
Yes.
So it is my proud privilege to introduce Dr. Samarjit Kar, and let me just tell about the Samarjit Kar. Professor Samarjit Kar is currently a professor in the Department of Mathematics, National Institute of Technology, Durgapur, India. He served as head of the mathematics department at NIT Durgapur from July 2011 to June 2013, July 2017 to June 2019. He received his PhD degree from Vidyasagar University in 2001. His current research interests include operation research and optimization, soft computing, machine learning, and uncertainty modeling. He is also an active participant in Chinese academia, having served as a visiting professor at Tsinghua University since 2009 and as a co-investigator of two sponsored projects funded by Natural Science Foundation of China at Tsinghua University and Nankai University. He has published over 200 referred articles in international journals and authored 6 edited book volumes in Springer. Presently, he is acting as secretary to 11 Operational Research Society of India, Kolkata chapter. And with that introduction, I will be inviting the Professor Samarjit Kar to deliver his plenary talk or invited talk. It is a plenary talk basically. And Professor Samarjit Kar, please.
Good morning, Professor Datta and Professor. So good morning to all of you. So at first, I convey my sincere thanks to the organizers for giving me this opportunity to give a talk in this international conference. I'm really very happy to be here today. So my today's talk is on uncertain multi-objective minimal spanning tree problem. So actually, let me share my screen first. Just 1 minute. Is it visible, sir?
Yes, it is coming.
It is coming.
Yeah, it has come.
It has come.
Okay. So actually, during last few years, we are working on uncertainty-based modeling for network optimization problem, and especially for multi-objective network optimization problem. And in this talk, actually, I give you the idea of network problems, especially minimal spanning tree problem, because during a few years, there are a lot of applications of minimal spanning tree problem in various different directions, like transportation modeling, brain computing networks, clustering analysis, image analysis, disasters management, so many areas. So, and already there are few works in different uncertain domains for minimal spanning tree problems, like fuzzy based minimal spanning tree problem, fuzzy rough minimal spanning tree problem. But there are very few works on multi-objective domain, especially in network optimization problem. So our main goal is to develop the multi-objective network optimization problem for different areas, like minimal spanning tree problem, um, maximal flow problem, traveling salesman problem, vehicle routing problem. There are so many network problems, and which has lot of real applications. So here solving also there are different uncertain domains, like fuzzy, type 2 fuzzy, because in the previous lecture already we have the idea of type 2 fuzzy systems. Also fuzzy rough system, fuzzy random system. And here basically my main target is how to develop such type of network problems in Lewis uncertainty based optimization problem. So actually, in 2007, Professor Bording Liu gave the idea of uncertainty theory, which is different from stochastic theory as well as fuzzy theory. So at first, I gave you a small idea of Liu's uncertainty theory. Then how we develop this type of multi-objective network optimization problem, especially minimal spanning tree problem. Then there are different solution approaches, because for multi-objective domain, there are some classical approaches, but if we use those classical optimization technique, mostly we converge a single optimal solution. But in multi-objective optimization, always our target is to have a set of solution. That means set of compromised solution, because we cannot get the optimal solution here. So obviously we can use some meta-heuristics algorithm by which we can solve such type of multi-objective problems. And finally, because we have used several evolutionary algorithms or several meta-heuristics algorithms, so we have to compare their performances through some statistical measures. So at first, in uncertain network models, so there are a lot of network optimization problems arises for practical region, like shortest route in traffic or communication network, establishing cost-effective communication network, maximum of capability of flow problems, shortest routes, supply-demand problems, and many areas. So these network problems having different structural characteristics and model for numerous applications. And why uncertainty is important in such type of network problems? Because if we consider any this type of network problems, always there are cost, time, and others associated. But always some uncertainties are there in their time schedule or different cost parameters and others. So such type of problems, such type of real life network problems, to tackle these uncertainty, people can use different types of uncertainty based approaches, like fuzzy set theory, rough set theory, uncertainty theory, and also some hybrid approaches. So here main goal is to develop network problems with different uncertain parameters as uncertain variables. For this particular problem here, I use uncertainty theory based approach, which is neither randomly, we cannot deal either in stochastic approach or fuzzy approach. So the main objectives of this model, here we consider an uncertain multi-objective minimal spanning tree problem, where to minimize the overall cost and time between the vertices of the weighted connected network. Basically, here we consider some data set, from a transport company, which company facilitates their bus services in a city. And in the course of journey, this company offers an attractive payback for their bus services up to 500 rupees if the estimated travel time delayed by 45 minutes. So by using that data set, because there are uncertainties in time due to some congestions and other things, so they can allow maximum 45 minutes delay time for their course of journey. So accordingly, we can design this spanning tree problem, basically bi-objective spanning tree problem, where our first objective is to minimize the cost and second objective is to minimize the time. And obvious, since there are some uncertainties in time and cost, so obviously this is an uncertainty based model. And before developing the mathematical model, we for solving this uncertainty based multi-objective minimal spanning tree problem, we use two types of two techniques, that is expected value model and chance constraint model, for transforming this uncertainty based model into deterministic one. Then this deterministic problem has been solved by different approaches. Firstly, we use a classical based approach, that is very well known approach, epsilon constraint method, and two multi-objective genetic algorithm. One is a non-dominated sorting genetic algorithm. This is known as NSGA2, proposed by Kalyan Moidev, and another approach, that is another evolutionary algorithmic approach, that is known as DENSIA. This is also very popular multi-objective evolutionary algorithm, which is mainly dealt with discrete types of problems like network problems. So before going to the model, just quickly go through with this uncertainty theory. In 2007, Liu proposed this uncertainty theory by these four axiomatic definitions. So in 2009, he also adds one more axioms, that is product axiom. So first three axioms is similar to the random theory, that means normality, self-duality. Here countable subadditivity, but in the case of random theory it is equality. And for the product axiom, he considered this product of the events, a measure of the product of the events is product of the corresponding measures. So then he defined uncertain variable and the corresponding distribution like probability theory. So uncertain variable xi is basically a function from the uncertainty space to real number, similar to random variables he defined. And then also defined the uncertain distribution by this function. This is a measurable function with xi less than equal to x. Accordingly, you can define that expected value of xi, that is 0 to infinity m of xi greater than equal to x dx minus infinity to 0 m of measure of xi less than equal to x. But why this? What is uncertainty? So here it is different from random uncertainty or fuzzy uncertainty, because already we know random uncertainty is basically depends on chance, and fuzzy uncertainty depends on similarity. But here, say in this example, you look, if we consider the number of students in a class is about 8, that may be 7, maybe 8, or maybe 9. Accordingly, if we define the corresponding measure, so obviously there are this many events are there, and if we define this measure as by these numeric values, so obviously all the previous 4 axioms are satisfied. So obviously we can define it as a uncertain variable. But why such type of uncertainty is important? Here I just quickly gave you this example, and because of sometimes in probability theory, if historical data sets, that means that completely then obviously random theory is the best choice. But sometimes due to the lack of data. So in that case, we should invite some domain experts to evaluate their belief degree for the each event. So in the first figure, in this look, if the data set is completely known, that means historical data, then obviously the probability is the best choice. But in the second case, where the data set is not known clearly, or maybe due to some economic reason and other things, then obviously we should invite some domain experts. So in that case, obviously we can deal with this uncertainty theory. So in this example, you just look, if we assume that the weight of a truck is 90 tons and the strength of the bridge, the strength of 50 bridges are identically distributed random variables, which is normally normal random variables having mean 100 and variance 1. And if we consider the probability that the truck can cross the bridge over 50 bridges, obviously it is the probability value is near to 1. But when there do not exist any observed data, so here data is observed because all the data is given, so in that case probability value goes to 1. So usually the belief degree has much larger variance than the real strength of the bridge. So because there is no experimental data sets are there. So in other words, if we consider this, the belief degree looks like a normally distributed with 100 mean and 100 variance. If we want to deal with the same problem, that means we have similar 50 bridges which are identically distributed random variables. And now if we have the track process over the 50 bridges one by one, then if we measure the corresponding probability, just completely reverse, it goes to near, the probability value goes to 0. So because that means the law of large number is not hold in this case. So thus almost impossible that the track process over the 50 bridges successfully. So therefore it leaves some contradictions with the previous result. So given in this Lewis book, if you are interested, you can go through that. Now we come to our problem. So here there are some literatures which are deal with uncertainty based minimum tree problem, but no one have considered multi-objective minimal spanning tree problem, because if we consider some real life problems like bus route problem or clustering analysis or brain computing network, there are some applications where always we deals with some multiple criteria or multiple objective. So here the main flow of our work is, first we consider this minimal spanning tree model this problem, then we transform this uncertainty based model into deterministic one by using expected value model and chance constant model. Then we use two types of solution methodology, one by classical approach and other two by evolutionary algorithmic based approach. So this is our problem definition. So mathematical model is very simple. You look, there are two objectives are there: minimizing the cost, first objective, and the second objective is minimizing the time. And having two constraints, the first constraint is basically for the tree constraint, that is number of edges equal to number of vertices minus 1, and the second constraint is the loop elimination constraint. That means there is cycle elimination constraint. So here you just look, the sum of xi is less than equal to mod k minus 1, obviously k greater than equal to 3. That means we cannot consider consecutive 3 edges or more edges which can make a cycle. So this is a very simple mathematical model. So now for the expected value model, we just consider the expected value of the first objective and expected value of the second objective. And already I show you the mathematical formula for expected value of a random of an uncertain variable. So easily we can determine this transformation of the expected value model. Similarly, for chance constraint model, for minimizing the cost by traveling time through the edges, having a confidence level at alpha 1 level, and for the second objective, another confidence level. If we fix these two confidence level, alpha 1 and alpha 2, then the corresponding model is transformed in this way: minimize Z1 bar, minimize Z2 bar subject to these two constraints, and other tree constraints are same. So here we use two different non-dominated sorting algorithm. I am not going to the detail of that. This is because this is well known. So I just skip this part. So now for the result part, because already I told you here, we used our proposed model as initially a smaller network, and then we solve the real life problems, that is a bus route problem. So obviously that though the part of this result already published in an international journal with this example, but that real application part we have not yet finalized. So maybe very soon we can finalize those results. But what is the concepts, how to determine the result? I will show you this. So this is a simple weighted connected network having 10 vertices and I think 16 edges. So for this network, we are considering the edge weights, two different edge weights. One is representing the corresponding cost and another is representing the corresponding time. So this is uncertain cost parameters. Here we consider this zigzag uncertain variable because Liu proposed different types of uncertain parameters, like different types of uncertain variable, that is zigzag uncertain variable, linear uncertain variable, normal uncertain variable, log normal uncertain variable, similar to probability distribution. So here we consider zigzag type of uncertain variable. So these are the cost parameters for zigzag uncertain variable. Similarly, these are the time parameters for zigzag uncertain variable for different edges. And by using expected value model, we consider we find the expected value of the cost value is around 631.55, and the time value is this. And the corresponding minimal spanning tree, because here the number of edges is 10, so obviously the tree minimal spanning tree containing 9 edges. So these edges are considered for this expected value model. And similarly for the chance constant model, the result is little different at 90% confidence interval, considering that confidence level as 0.9. So Z1, Z2 values are given here, and the corresponding minimal spanning tree is this. Similarly, because here in the previous case, we use the simple classical based approach, that is global criteria method, and the corresponding solution is given here. But in the case of evolutionary algorithm, we have used two different evolutionary algorithms. One is NSGA2 and Densia. And for the first evolutionary algorithm, we get different solution points in the non-dominated front. And also for Densia, in here you look in when we use this Densia, so we get more solution points in the non-dominated front. But one thing is important: out of those set of solutions, one solution matched with the previous solution, because already I told you, if we use some classical based approach, generally we get a single solution. But in the case of evolutionary algorithm, there is a set of solution, that is a non-dominated front, and one solution is matched with the solution of the classical based approach. So that is shown in the red line. And if we plot those solutions in this front, in this graphical representation, so here you can easily determine, because both are minimization constraint, that means cost minimization as well as time minimization. So your front is here, the front is looks like, and the solution for epsilon constraint is given here by this red mark. Similarly, for the second figure shows the solution of through Densia. Here the number of solution is more. than the NSGA2. And for comparing those results, here this is for the solution for CCM, that means chance constant problem. And similarly for graphical representation is also given here. The next figure is given for the different pair of alpha levels, because initially we consider both alpha 1 and alpha 2 as 0.9 and 0.9. So if we change this alpha level from 0.2, 0.4, 0.6 for both alpha 1 and alpha 2, so obviously this is basically a sensitivity test for the different chance level. So now when we solve this type of problems by using different meta-heuristics algorithm, so obviously we have to compare through some statistical measure. So that means which algorithm perform better than the other. So here we consider 4 different statistical performance matrices. One is inverted generational distance, epsilon, hypervolume, and spread. So and for the first, that means that first measure, that is hypervolume measure, the greater value is more acceptable, but in the case of spread, lower value is acceptable. Similarly for other two. So by comparing these results for the both case of expected value model and chance constant model, we can conclude that Densia perform a little better than the NSGA2. So in the conclusion, so here obviously we believe that our model extend the ability to multi-objective minimal spanning tree problem from the uncertainty based multi-objective minimal spanning tree problem through multi-objective minimal spanning tree problem. And here we consider this uncertainty based multi-objective problem through Liu's uncertainty measure. And the model explores a multi-objective spanning tree of a weighted connected undirected graph, which considered minimization of total cost and minimization of the total time through graphical simulation. And obviously we formulate both uncertain expected value model and chance constant model to solve this proposed model. And here one thing is very important, that selection of a single solution from the set of solution, it is very difficult, but decision maker always wants to a single solution. Sometimes people can use some classical based approach like epsilon constant method and others. But it is suggested that mostly the preferable suggestion is we can always use some evolutionary algorithmic approach, because here the set of solution is important. So that's why here we use 2 multi-objective genetic algorithmic approach, that is NSGA2 and Densia. And in future, we'd like to extend our model in uncertain random domain, because there already exists some single objective uncertain random network models like uncertain random minimal spanning tree and uncertain random maximal flow problem. So we want to extend that model into multi-objective model also. And one thing is very important, this type of multi-objective nature of the proposed problem characterized as a NP hard problem. So that means the solution, so getting the solution of such type of multi-objective minimal spanning tree problem is really difficult to solve by using the classical approach, because already there are so many leveling algorithms are available for such type of network problem, but it is very difficult to solve by that type of leveling algorithms or other classical method. So that's why always the best way to try to solve such type of uncertainty based model through evolutionary algorithm. So with this, these are the references. Thank you all. If we have any questions, maybe.
So I think now that the talk is open for the forum. Is there anybody to ask the question? You can directly ask to Professor Samarjit Kar. I hope that it is a good talk, and really I enjoyed also with the various techniques, And thank you once again to Professor Samarjit Kar on behalf of me and the organizing committee. So questions are to
Thank you,
be
sir.
asked from the audience. Yesterday also I have seen that the response towards the questions is not that enriched. I do not know what the students they are doing. I think they must have got their PhD degree. Students are referring to that. Please ask them some questions. So if there are no questions, then I think that they will give a big
Just
hand.
one question,
Yes, yes,
please. Yeah.
Yes, yeah.
Dr. Kaur, I want to know what is the difference between Liu's concept of uncertainty and what is called Zade's uncertainty?
Yes, so in Jade's uncertainty, it is completely depends on similarity. That means that fuzzy similarity, that means how the event are similar. So that means it represented through the membership function. Okay,
Okay.
but that means Jade first defined uncertainty through the set, then its measure. But Liu starts with the measure which is similar to the probability measure. That means it follow the 4 axioms. That means normality, subjectivity, productivity. So which is completely depends on the belief degree. It
Okay.
is depends on the expert's opinion. Okay.
Okay. Okay. Nice.
In that case, I would like to ask one question.
Yes,
Because
yes.
every student at the postgraduate level, they will know that the Heisenberg's uncertainty. So Heisenberg uncertainty is nothing but the deviation from the location coordinate multiplied by the deviation from the position momentum coordinate. If we do the multiplication, I will get that product is equal to less than equal to h by 2 pi, where h is known as the Planck's constant. Now, the Heisenberg uncertainty, is it the Liu's uncertainty or Jade's uncertainty?
I'm not completely
No, no.
sure about that.
Sir, I think that uncertainty has no way with the Jade, because I have
Yes,
heard
yes, you
some
are right.
I have heard some lectures.
Yeah.
They are always saying probabilistic uncertainty,
Yes.
not that
Yes,
type of uncertainty.
Yeah.
Heisenberg uncertainty is not there.
Yes.
That
yes,
is
you are
no way
right. You are
related to
right.
Heisenberg uncertainty, I
Yes,
think.
yes,
Yeah.
yes.
So Heisenberg
Because
uncertainty basically is probabilistic uncertainty.
when we use Heisenberg's uncertainty, then obviously it depends on the historical data. That means data set is available in that case.
So that means that the uncertainty cannot be described by the Jade's uncertainty. We cannot describe by the delta x
Yes.
position uncertainty. We can describe, na? Because when you are giving the motor control speed, we can describe, because speed is nothing but the velocity, and if the mass is having, so we have a momentum. So momentum uncertainty is there. So Jade's uncertainty can be there with the fuzzy uncertainty. So that means we can develop a new branch of science called fuzzy quantum mechanics. We can develop that, because that student, that the next generation should look at how the uncertainty can be brought back into the picture, where a lot of application oriented problems can be developed.
Yes.
Like fuzzy quantum mechanics is nothing but the fuzzy quantum fluid, which will be used for reducing the petrol cost, which I have seen because there are many possibilities are there. And like Dr. Shubit Das done the fractional calculus, and there are application fuzzy fractional calculus.
Now it is
So
coming. I have seen
now it is coming.
some
No?
papers.
So
Yeah.
therefore, we can do that the fuzzy quantum mechanics also, so that mixture of the Lewis uncertainty and probabilistic uncertainty can be given in a very good domain.
Correct.
Because today Professor Castillo gave the type 3. So that means like Omicron variant, we may have a type 4, we may have a type 5. So
Yes,
we have
theoretically that is possible. Yeah.
theoretically that is possible. Then definitely that when is applied to the robot may be application of the type 3 fuzzy set, type 4 fuzzy set, more like drone can fly. So like that, this application this student can think of, because we are having an old age, so as students they will be facing the quantum computing, then at that time they should face this kind of problem. Once more, thank you, Professor Samarjit Kar, and give a nice talk illuminating that there is a lot of new concepts. And I hope that the Professor Liu also will be very happy, at least that you are the person who is addressing the Professor Liu's uncertainty.
Thank you, Dr. Datta.
Okay,
Thank you
sir.
all. Okay.
Now it is the responsibility of the organizing committee, Professor Shom. I am handing over my responsibility to you. Please.
Thank you, Dr. Datto, for handling the last talk, and thanks to the speaker, Professor Kaur, for giving a very illuminating talk. Now